All right, so welcome you guys. If you hadn't seen me before, this is me, Conrad Diaz. I am the founder and the lead instructor for these lectures. Okay, let's go ahead and jump right into the topics. So you must have read the email, and these are the topics that we're covering. Okay, so let's jump right into it. We're talking about how to get clever, how to get creative with machined part design. But these lectures are not necessarily advanced. They cover advanced topics, but we also cover a lot of foundation. It's important for an academy to teach foundation, basics, intermediate level material, all the way up to advanced. So we have to start at the beginning briefly because we only have about an hour. We're gonna cover some basics of machined part fabrication for those of you that are not already very familiar with that. There will be some sketching along the way, and also I'm going to be showing SolidWorks, some SolidWorks models and assemblies to you guys. Okay, so machined part design. I would like to think, I'm not going to spend too much time on this. I imagine most of you or all of you already know how machining works. You have a cutting tool that spins, and when it rotates, it removes material. And you have hundreds, if not thousands, of different standard geometries for these cutting tools in order to remove material. So machining is a process where we remove material to arrive at a final geometry. That's different from an additive process, such as 3D printing, where you're adding material to build a geometry. In machining, we do the opposite. We remove material. So let's see. Just really quick, I'm going to be jumping in and out of the internet because, as I keep telling you every single time, part of being an excellent engineer is not only knowing how to design well and how to have knowledge and experience, but also when we don't know something or when we do not have experience on something, we need to be able to know where to go, how to find it. Where do we go to find it? Usually we end up in the internet these days. But even if you know how to use the internet very well, here's another challenge when we're starting out. What do you search for? What are the key terms that you're going to search for? So, throughout these lectures and in our professional certificate programs, we do a lot of real world activities, as if you were really designing something and you run into something you don't know. We give you terminology, we look it up on the internet, and we go from there. Okay, so in this particular case, it's straightforward. It's just machined part design, and I'm just gonna pull some images real quick. So of course, this is what machined parts look like. And here, this gives you a very clear picture of what's happening. You have, in this case, a milling machine that is holding a cutting tool. And as the cutting tool rotates, it removes material. So one very basic thing for you to realize and always keep in mind in machining, at least for this kind, general, conventional, and CNC machining, you have a rotating tool, which means you cannot have sharp corners. If you look at the geometry on the left, we're not able to machine that in any kind of conventional, typical way, because the cutting tool is rotating. So as it rotates, it's going to leave a radius. In CAD programs, usually call it fillet. Okay, so if that's new to you, well, you're in the right place, where we're going to move on from here into a little bit more advanced stuff, gradually, here and there. So let me show you this model real quick. And let's see, hopefully I have 3 computers running, and this one with SolidWorks has got a lot of things open. So I'm really hoping that it's going to be able to keep up with us, not have any computer related issues. Let's see, we'll be we will be talking about this one here. Well, this is not what I wanted to show you right now. Okay. We'll go back to SolidWorks in a moment. So that's one of the things to keep in mind about the manufacturing process when it comes to machining. So cost-saving considerations when you design a part for machining. First thing is we always try to stick to standard tools. If you have holes, for example, that's a very common example. You have a hole of a certain diameter. If it's not a critical type of situation where you need a custom diameter hole, you should stick to standard diameters. Counterbore holes, same thing. So if this is new to you, once again, let me show you some images. All right. Sometimes I get confused between all these keywords and mice that I'm working here with, but let's have a look at this. So look up standard drill sizes, for example, and images. Now, do keep in mind, there's a lot of misinformation or bad information on the internet. So you do have to be careful as to where you're getting this information from. You have to do your best to figure out if it's reliable information, and eventually conduct your own testing. Nothing beats testing your designs thoroughly for functionality, etc. But as far as locating information that you may use in your designs or reference information, try to make sure that it comes, in this particular case, from reliable companies that have been in business for a long time, that are experts in their field. And even then, you know, we all make mistakes, but chances are you're increasing the possibility that the information you're getting is accurate. So for example, we have this table here, drill sizes. So again, if you don't need a custom size, go with something like this. Something a little bit more interesting is counterbores. Let me show you this. Now we can go into SolidWorks, as long as I get out of the way. So this is a fixture, and we're zooming in on the base plate, for example. So the base plate, you will notice, has counterbore holes. That is for to use threaded fasteners to attach the base plate or the whole fixture as a whole to whatever it is we're attaching it to. A table, another machine, a CNC bed, whatever we're attaching it to. These are counterbore holes for that purpose. Your CAD programs, if they're sophisticated and modern enough, usually let you choose quarter 20 socket head cap screw, for example, and it'll give you a choice of low clearance or loose clearance, or whatever terminology they use. Usually that's those standard dimensions that your CAD program will recommend are in alignment with standard tooling, so you can be safe in that regard. But now let's look up, let's see, counterbore drill bit, so that you can see exactly what it is that I'm talking about. So this one here, for example, this is a cutting tool for a counterbore hole. And you can see that it's gonna, actually this one is just only going to counterbore the hole. It doesn't look like it's going to also cut the pilot hole, the smaller diameter hole. Let's see. See if I find one that would do both. This one here may do that. So it looks like the idea here is that during the machining process, you would not drill the pilot hole, which is this one here. That is the smaller diameter hole, which locates the threaded fastener. And this is the bigger inside diameter hole, which holds the head of the screw, of the threaded fastener, okay? So when we're talking about the pilot hole for the screw itself, during the machining process, they usually don't start with that drill bit, that size. They start a little bit smaller. First thing is, I think it's called a center drill. You get the location and just the initial location of the hole going with a center drill. And then you go drill it a little bit, then you might drill it out a little bit bigger, and then switch drills a little bit bigger, depending on the size. So you have an initial pilot hole, and then you can introduce this tool, which will finalize the hole for the screw, and then after that, machine the counterbore portion. So it's almost 2 holes in 1 step. Okay, but the point is standard tools. All right, let me see if you have any questions. I try to keep my eyes on everything here at the same time. Will there also be references so we can dive deep into the topics? So Omar, these sessions are about 60 minutes to 90 minutes at the most. So we try to pick specific topics, and then we cover subtopics surrounding the main topic. We do not have enough time to get deeper and deeper. Where we do that is in the professional certificate programs, which I mentioned last week. Right now they're closed, but we're about to open them up again in a couple of weeks. So if you go to the main website, mechanicalengineeringacademy.com, and you click on certificate programs, if you haven't done that already, you can learn about 2 of our flagship programs that we have going on right now. Let's see, just really quick. It's a long page with a lot of information. And we have a foundation program, and we have also a more advanced program, which is foundation plus automated systems. And it covers a lot of material, and this is where we go a lot more into depth into the topics. Okay, it's a professional level certificate program. Any other question here? Video file not found. Problem occurred. What video file? You may try to refresh your browser or click on reconnect in the window that you guys are watching this lecture through. Toward the top, it says connection problems, ? Then it says reconnect. You can click on that, and it usually helps and brings you back. So you meant recommendation references so that we can read them, so that you guys can read them. Every topic that we cover, to some extent, you can find reference information on the internet. As far as machining, I would get my hands on very good textbooks or reference books, whether it's the hard copy or the PDF or the Kindle version. You know, that now they have all these electronic versions. Look for design for manufacturability. That could be your search term, or design for machining. And you will find a lot of information on this. Okay? All right. Oh, this and just about any topic you can think of. Let's see, where were we? I want to cover a lot, so I want to try to go a little bit faster. Another way to save costs when you're designing machine parts. You got to keep that in mind as you design, not just functionality, but defining cost-effective systems. That's important. You can take, there are times that it makes more sense to break a single part into 2 parts. And I'll give you a quick example here. Let's just sketch something. We're going to sketch something here real quick. So all right, a quick example of this. This looks different. I think Microsoft just updated my PowerPoint. Okay. They moved things on me, but let's try. Let's see. All right. So if for some reason you need a part that looks, let's see, do it this way. You need a bracket type geometry that looks like this. Okay, and it's got holes and whatever other features it needs to have. You need to be able to look at this geometry and consider that and realize that during machining, once again, it's a process where we remove material. That means that the piece that we start with is a bigger piece, and it's going to be a large block like this. So that would be the starting point to end up at such geometry that you're after. In this case, that means that looking at the geometry, they are going to have to remove a lot of material. All of this material here will have to be removed to arrive at that angle-shaped geometry. So this is one case where you, with experience and making sure you pay attention to these details, you would realize it's probably more cost-effective to break it into two parts. So I would probably make a part like this, one part like this, and the other one like this. So now we have designed two plates, basically, joined together by some means, usually threaded fasteners, okay? So that's what we mean by the possibility of breaking parts into multiple parts when it makes sense to reduce costs. All right, I'm gonna copy this slide. I will be emailing this presentation to you guys. I didn't do that last week because there wasn't really a lot of value, I think, in the presentation last week. But in this one, we're gonna be sketching a lot. And I think that some of you would like to have these sketches and this presentation. Okay, so now we're gonna talk about single machining setup versus multiple setups. We might jump in the internet and see if we find a couple of good reference images. So let's see. Let's look up single machining setup. I don't know, versus multiple setups, maybe. CNC. Let's see what comes up. We might find something good. And images. If we don't find something good, I'll sketch it for you just to make sure the point is clear. All right, let's do this. Let's talk about this image here. So here in this particular setup, obviously they are it's a CNC machine, and they have set it up to machine multiple parts at the same time. Most likely all of those parts are identical. So it looks like 16 parts, all identical, that are being machined simultaneously. So single setup, in this particular case, what I mean is, if you look at the setup here, the machine, the one of the parts, just focus on one of the parts. It's oriented in a specific orientation, and it's being machined from above. If this part has features on the side, holes that go sideways, let me do this. I think a lot of this is clear, but I want to make sure absolutely certain. I want to make sure that you fully understand what we're talking about. So I'll do a quick sketch here. Okay, so we've got this set up here. So with a color you can see. So it's being machined from above with the cutting tools. But let's say the geometry you designed, for some reason, you have to have it that way. There's a slot here, and maybe that slot goes all the way through to the other side. Okay, on that back wall. So oriented the way it is, they're not able to do that. They would have to flip the machine on its side and then machine that feature. So we have designed a machine that not only, that in this particular case probably requires two setups, one facing up and then a 90-degree reorientation. And sometimes you can't avoid it, but whenever possible, keep that in mind. If you can design parts that can be machined in a single setup, that helps with cost reduction. Let's see. Question here: which is better, fasteners or welding? And can you please explain why? Okay. I guess it's somewhat on topic, so I'll take a moment to talk about that. Thank you for that question. Threaded fasteners, for one thing, you're able to remove them. So, for example, if you're designing a machine, you need to assemble the machine, you need to test it, you need to be able to revise the design as you go. Not all the time. I mean, it happens sometimes that you design something and it works like a charm the first time around. But quite often there's troubleshooting to be done. You need to revise the design. So to be able to disassemble the design, threaded fasteners are very handy. Welding, of course, tends to be a permanent solution. When you already have a design that you know you're not going to need to disassemble. That's one reason to pursue welding instead of threaded fasteners. I'm just going to leave it at that. I hope that gives you a little bit of an idea, but I'm going to move on so we can stay a little bit more on topic, okay? And at the end of the lecture, I can stay a little bit longer if you guys have questions that are not necessarily on topic. Let's see. Material selection, of course, matters a lot. You have the materials cost different things, different prices, right? But not only do you have to consider the material cost itself, but also how easily is that material able to be machined. If you're machining Delrin, for example, it's a type of plastic, very easy to machine. Every material has pros and cons, keep that in mind, and not all materials are suitable for your particular application. But usually, taking in consideration the restrictions of whatever it is you're designing, you can arrive at multiple material choices. Okay, I think it's rare when we run into a situation where there's only one material that will work for an application. You have multiple choices. So among those, you can keep cost in mind, and if it makes sense, choose the lower cost material, easier to machine and things like that. Okay, and of course there are other factors that come into the picture related to cost considerations. Okay, moving on. Machined features to locate parts. We're just going to be very brief. Remember, this kind of thing we spend hours in the certificate programs discussing and teaching you. But here is a brief overview. So, machine features to locate parts. One basic approach, if you're using threaded fasteners, is to use the threaded fastener itself to locate the components. No other feature, just the threaded fastener. You tighten it, and that's how you locate the components. So let's look at SolidWorks for a moment. I think this one is relevant. Let me have a look here. Let's see, zooming out. Particular case, the base plate, for example. We don't need this here. The base plate, for example, it just has counterbore holes for some kind of socket head cap screw, and it's being attached to a bed of another system that looks like a CNC machine. So the locating of this base plate relies solely on the threaded fasteners. No other feature for that purpose. The same thing applies to this gusset or vertical plate over here. If we look underneath, once again, it's got socket head cap screw holes for the threaded fasteners that are going to go from underneath into that vertical plate. The only thing locating that vertical plate in relation to the base plate is the threaded fasteners. Okay, let's see one thing. Okay, we'll come back to that in a moment. So that's one very basic way to do that. That's usually for non-critical applications where you don't require precise positioning of the parts in relation to each other. Another approach is using dowel pins. If you're not familiar with dowel pins, let's go back over here. Whoa. Okay, quick search here, dowel pins. They're cylindrical pins, usually metallic, that help you locate components. Well, they have many purposes, but one of them is to help you locate components. So they look like this, just a very basic dowel pin. And you can use these guys in the following way. Another quick sketch here. Let's see. You have, how do I want to do this? Let's say we have a plate. Oh. We have a plate here. Let's call that a base plate. And we want to attach another plate vertically to it, okay? But we need some level of precise positioning. Relying on the threaded fasteners would not be sufficient. So one way to do it is we would press fit or interference fit dowel pins. You would usually go with 2 of them. And underneath the other plate, of course, you would have, let's see, you would have matching holes to accept the dowel pin. Okay, so that's the basic idea. Now, this is very simplified. I mean, this kind of approach may work for woodworking and things like that. It's suitable for that kind of a thing. If you just leave it like that, just dowel pins and drill holes, and then use some glue and join your pieces together. That may work just like that for woodworking. When we're talking about machining, we have to pay a lot more attention to specific details. If you're looking for precise positioning, you have to take in consideration manufacturing tolerances. So the dowel pin itself is going to have a diameter that varies. It's never precisely 0.125 inches with infinite decimal point places, 0.125 exactly. That's not how it works. It might be 0.125 between, let's say between 0.1250 and 0.1253. That's a manufacturing tolerance. So it's got its own manufacturing tolerance. The hole that we drill, let's say over here, has its own manufacturing tolerance. You're using a drill bit, it's vibrating, it's shaking a little bit. Even if you use a reamer, which produces a more precise hole, it's got its own vibration, its own imperfections, its own manufacturing tolerance. That the entire machine you're working on is not 100% perfect. So the resulting hole from drilling and even reaming will have its own manufacturing tolerance. And then you keep thinking about these things. These are principles that are essential for us mechanical design engineers. The location from center to center of these two holes also has its own manufacturing tolerance. It's not going to be precisely 2.00000 inches. It just can't be. It'll have its own tolerance, perhaps 2 inches, and we might specify plus minus half a thousandth of an inch. Okay, so when you keep in mind manufacturing tolerances, then you start to run into potential issues if you use 2 round pins and 2 round holes. So here's one way to work around such issues in a somewhat clever way. Let me see. So guess what we're doing? We're going to the internet once again. Because I'm pretty sure we can find a relevant image here that will save us time. Let's see. Let's look up Dowel pin, diamond pin. You should become familiar with that for location. Let's see what comes up there. You should be familiar with the what's called a diamond pin. We'll talk about diamond pin and also a slotted hole. Okay, so images. Diamond pin looks like this one here. So in this particular design, there is a round hole on the right, which if you can visualize it, and originally we had two round pins and 2 mating round holes. So 1 round pin is going to go into its mating hole and locate the part to some extent, right? The part will still be able to rotate if that's all we have. Diamond pin on the other end, if you can visualize that, and I'll show you another image right now, it goes into that round hole and it keeps the part from rotating. But the misalignment due to manufacturing tolerances is not too much of an issue because the pin has been relieved, material removed from the right side and the left side, as you see here. So the center to center dimension of those 2 pins can vary a little bit. It doesn't have to be as tight. It can be a looser tolerance, which reduces the cost, and it will not affect the ability of this arrangement to locate the part precisely. Okay, this one will make a little bit more sense. Let's see. Oh, sorry. Let me see, before I click on that one, let's see if there's something. Okay, this one shows a top view. So we have the plate already assembled, I believe, on these 2 pins. So the pin is on the right is round, the hole is round as well. It locates the part, but it can still rotate. But now we have a diamond pin on the left going into a mating round hole. So you can see that the part can no longer rotate. But if we vary the center to center dimension between these 2, it's okay. There's a little bit of wiggle room for that. So that's one way to reduce the cost. Whoop. Clicked on that accidentally. Okay, I hope that's making sense. One last image in case you're not following that. Let's see. But I believe you are. Let's see. Go ahead and type in, please. Let me know. Is that point pretty clear, or do you need me to elaborate a little bit more? While you do that, we're going to talk about the one other alternative, which is, oh, what happened? 1 second here. Okay, so let me, I'm waiting for you guys to let me know if that was clear, or do you need me to spend more time on that particular approach. So the alternate approach to that, instead of having a diamond pin hole, diamond shaped pin, which can be costly, they're usually hard pins, and they have standard sizes, and it's a little bit hard. They're a little bit higher in price. Okay, it's clear. Good. The alternative that I'm going to leave you here, I'm going to sketch it, and then I need to step away for a moment. Instead of a diamond pin, we could use a slotted hole. So let's do it this way. Oh. Why did PowerPoint change the approach? I don't like that. We have a plate here. And we can have a round hole, and we can have a slotted hole. So now the part that we're mating from above into this arrangement here can have 2 round pins. Let me do it this way. The pins going into these locating features can be round. And you can see how we're addressing the issue of center to center dimension. It doesn't have to be as tight. The round hole, let's do a top view real quick. Looking from a top view, we have a round hole, a slotted hole, and one hole, one pin will go inside like that. The other one can be here, or it can be a little bit to the right, or it can be all the way here to the right. So center to center dimension of that hole can have a looser tolerance. And as a general rule, looser tolerance translates into lower cost. All right, you guys, give me a moment. I'll let you think about that for a moment. Actually, I'm gonna leave you looking at this design here. Try to just absorb it a little bit by looking at it while I come back. I need to step away for a moment, but I'm gonna zoom in here. Let's see. Okay. It may be confusing to just look at it like that, but look at it for a moment, and I'll be back and we'll talk about this. All right. So let me know if you have any questions so far. So this is a fixture that I designed a long time ago, and I actually don't remember exactly. I remember in general what it was for and how it works, but there's some things I don't remember why it needed to be designed that way. So let's go over it real quick, and we'll cover machine part design as we go. So we talked about the base plate. I'm going to zoom in here. We talked about the base plate having multiple counterbore holes. You see that there are how many? And they're not even like at the corners of the base plate. There was a reason for that, because it was mating a table that it didn't make sense to put counterbore holes toward the back of the fixture. Okay. And obviously there's a redundant number of counterbore holes. There's too many. You really don't need to use threaded fasteners in all of those. But sometimes it makes sense to provide added flexibility. It doesn't cost a lot of money, extra money, to machine another 3-4 holes into a base plate, especially if it doesn't call for a separate setup. You do all these holes in one setup, so not too much cost increase in adding extra holes. So it's a matter of flexibility. I'll give you an example of a more a better example of flexibility, if you will. Looking down at the fixture here, let's see, I'm going to hide this because it's not too important right now. Oh, looks like I didn't make that into a sub-assembly for some reason. Okay. So, and take that away. So it looks something like this. And this plate over here is attached to the vertical plate in the back. This yellow plate moves up and down. I don't know how easily you can see that. I'm going to zoom in now. So you can tell that this is a handle here. It's a standard off-the-shelf handle for the user to grab it literally by hand and move this up and down. And the travel of that sliding plate is restricted by the slot right there. So we call that a slot or slotted hole, right? Just like the one we discussed a few minutes ago. So by hand, this is done like this. Now, I'm not going to get into the detail of what it was used for and the product and all that. It's not relevant at this point. It's a general overview, okay? But this sliding plate is spring-loaded. So it's continuously being pulled. If I remember correctly, it's pulled upward. I should have reviewed how I used it before showing it to you guys. But it's coming back to me. Let's see. Okay. I believe I remember. I'm looking for threaded holes because it used extension springs to spring load it. Sorry, bear with me. Interesting. I don't know if this is an earlier version. I'm not seeing the threaded holes for the spring anchors, but let's zoom in here. So this is the yellow plate that moves up and down. Okay, now we're going to talk about design flexibility. You see all these holes here, all these little threaded holes? These are for spring anchors, which spring anchors are used with extension springs. Let's see exactly what they look like. Spring anchor. Images. And they look like that. And they're tiny little guys, and it's a threaded component. You thread it into a threaded hole, and it provides an anchor point for you to hook whatever it is you're hooking. Like in this particular case, that's a kind of a spring that they use there on that anchor. Okay, hold on. Let me see. They don't have exactly what I want. Okay, but that's a spring anchor, and it's used for an extension spring. Okay, if you didn't know what those look like, it's these guys here. Okay, so they have two ears or two hooks or two loops at the end, and they're extension springs designed to be stretched, so they pull inward. Okay, so now you can see why you would need a spring anchor on both ends, and you hook the spring on both ends, and it gives you the pull force that you're after. So in this particular case, I do remember that during development, we did not know exactly what kind of force would be needed for this fixture. So it needed to be pulled upward from what I remember. So the way it was designed, and I did design this, it was, I remember there was a spring anchor here somewhere. I don't know if it's this one, but picture a spring anchor there. That one is fixed. It's not going anywhere, it's fixed. It provides support for one end of the extension spring. And then here, you don't need 5 spring anchors. You only need one more to support the other end. And you have a choice. You have a choice from 5 different positions to hook that extension spring. At each different position, you're going to get a different amount of strength. At the same time, another reason to do that was that there were only a limited amount of extension springs that fit the criteria that we were after. So, because you could say, why not just have 2 threaded holes for 2 spring anchors and change the type of spring that you use? That's sometimes doable. In this particular case, the selection of springs was limited. So one solution to provide design flexibility was to provide multiple holes. Even though we only have 2 or 3 spring choices, in combination that translates into 10 to 15 potential different strengths that can be chosen from. All right. So that's not necessarily machine part design, but it's related. Okay. See, any questions? No. All right. So I wanted to show you more here. So in this particular case, well, let me see what was next here. I'm going to stick to this so that I don't go way over time. It's already about an hour right now. So we talked about dowel pins and diamond pins, and instead of using a diamond pin, using a slotted hole on one end, okay, to address manufacturing tolerances and reduce costs of your designs. Another option is using a pocket. Again, if you're not familiar with a pocket, I'm about to sketch it for you. Let me copy this. Actually, just new slide. Okay. All right. So there's pockets for locating parts. Okay, so pocket is, I think, is self-explanatory, but if you're not familiar with it, we're definitely going to cover it briefly. Why Microsoft? Why did you move this around on me? Okay, so once again, we have a part. Let's use same idea of a horizontal plate and a vertical plate that we want to bring down onto it. Okay, we want to bring that down there. So instead of dowel pins, you would use a pocket, which is a shallow cutout that can accept the vertical plate that you want to put in there. And again, that's the general concept, but as a good engineer, you have to keep in mind manufacturability and all these things, tolerances, material. Okay, I'll get to that in a moment. I'm jumping ahead a little bit. So that's the idea. You have a pocket for your part to fit into it. This does not replace threaded fasteners, by the way. At the same time, you would still have holes and threaded holes. For your assembly. So the threaded fasteners would come. That's a perfect socket head cap screw right there. They would come from the bottom, okay, to assemble these together. So we're not talking about replacing the threaded fasteners. We're talking about more accurately positioning the parts in relation to each other. So you've got a pocket there, but we think about manufacturability, right? We had already concluded that sharp corners, such as those, are not possible, in general, not possible in machining, because you have a cutting tool that rotates, that spins to remove material. So if we try to program a CNC machine, milling machine tool to cut a rectangular pocket, instead what you get is a rectangular pocket with rounded edges. You would get something like that because of the cutting tool, right? So now we have a little bit of a problem. I'm sure you already spotted that. You have a rectangular pocket, or in this case, we improved the design because we recognize that it's a rotating cutting tool. That is awful. Do it this way. Okay, rounded corners there, but we have a rectangular rectangular vertical plate going in there with sharp edges. So we would have to shrink the design of the vertical plate to fit in there, and that kind of defeats the purpose. So a quick solution is to design reliefs for the cutting tool. In this particular case, something is typically done, you add, it's almost like a Mickey Mouse geometry. I run out of space. Let me do it right here. You would allow, this is a top view, you would allow the cutting tool to travel further than desired, like that. So the cutting tool can still travel. It would travel in here, but the resulting geometry is rectangular. And now you can have your rectangular piece fit in there without that being an issue. Okay, so keep in mind manufacturability, and these are pockets. As an alternative, you probably realized we could have let's see, what was I gonna say here? For this design here on the right that has rounded internal edges, an alternative is to chamfer the edges of whatever is going in there. Okay, so top view of that modified plate would be that's the top view of this plate over here, modified. We do chamfers on all four edges, and now it can fit into this pocket and probably locate accurately if we decided to do that. But more often than not, the approach on the bottom over here is what is used. Okay, moving on. I do understand if some of you need to leave, but I have a few more minutes and things to cover. And jump in if you have questions. You're welcome to. Let's see, did I cover everything on this one? Oh, I wanted to briefly mention locating shoulders for motors. Another thing, there's so many things. Something that we do a lot in design is integrate motors. If we have motion systems, we integrate motors into our designs. So how do we locate the axis of a motor if we needed to locate it accurately? Let's first look at a picture of a motor so you see what I'm referring to. Let's see. I'm gonna look up a stepper motor specifically because I know their geometry fairly well. Okay, for now we won't worry about what a stepper motor is and how it's different from other motors, but I want you to look at the geometry of these stepper motors. So you've got the motor, obviously you have the motor shaft coming out, and look at that right there. There's another diameter in the body, in the face. There's a diameter, there's a feature. It can be called a shoulder, and it's a locating shoulder. So that diameter, let me make sure you know what I'm referring to. This diameter right here is usually machined precisely with tight tolerance, and it's used for locating purposes. So now you can have a plate with not a rectangular pocket, but a rounded pocket. So I'm going to do a side view instead. So we've got the motor, shoulder, we're looking at a side view, and of course motor shaft coming out. Okay, there's the axis. So on the mating plate, where whatever you are attaching this to, or sometimes it's sheet metal, on that mating plate, you would have a tight tolerance hole. This one right here, a hole with an inside diameter and tight manufacturing tolerance. That'll accurately locate the axis of the motor. Hope that makes sense. So much to keep in mind, you guys, when you're trying to locate in this particular way, dowel pins or pockets, do keep in mind the following, and I think I do have a drawing open. Let's look at this drawing here. I don't know how many of you can you type in, let me know how many of you have already done engineering drawings for machined parts, not for school, but actually for work. Okay, type that in. I'm curious. And in the meantime, I'm gonna zoom in here. So this drawing is actually for this part over here. Let me open it by itself. So this plate right here is what we're looking at, the engineering drawing that we're about to look at. Okay, let's go back to the drawing. So what I want to talk about is precision diameter holes. For example, this hole over here. Looking at that hole right there, about the middle of your screen, its diameter is 377 thousandths. You can say it like that, thousandths of an inch, 377 thousandths of an diameter. Or you can say 0.377. There are different ways to say it. But look at its tolerance. First thing is, it's encircled in an oval. That usually means that it's a critical dimension. And it's just easier for quality control during manufacturing to see an oval, and you pay extra attention to that. And the manufacturing tolerance is plus 1,000th of an inch minus 0. So as a final manufactured part, that ID, inside diameter, needs to be between 0.377 and 0.378 inches in ID, inside diameter. Now, I bring this to your attention for the following reason. This drawing is from many, many years ago. I have since revised my approach. If we remember that if we lack good mentors, or if we have good mentors, but they just don't have the time to help, we don't necessarily learn details that need to be learned. We end up learning them the hard way, or we never learn them. So that's part of the reason why the Academy is here. I'm very interested in teaching proper design and engineering from the beginning, and with the certificate programs, packing a lot of valuable information in a few weeks, rather than waiting to accumulate that same information over years, the way most of us ended up learning this stuff. So I point this out to you. We're talking about a tight tolerance hole. Why are we talking about that here? Well, look at the finish on this part. At the time I called out finish black anodize. By itself, that's a very simplified way of calling out black anodize. I no longer agree. These days, I add a lot more detail to how I specify anodizing. Okay, we don't have time to go into that. But the point is, when you black anodize a part, it's a finishing process that not only builds on the surface, but it also penetrates the material. So going back over here, let's see. Let me do it on the hole here. I'm going to grab a... So Shane, you have designed, you have done machine parts and engineering drawings for work. Okay, that's good to know. I assume the rest haven't, or they're already gone, or they're eating something. I don't know what's going on. It's Saturday. That's okay. Doing the following here. I'm grabbing this. Okay. So you have a finishing process that is going to the black anodizing. The anodizing of this aluminum plate is going to build up on the surface, which means it's going to reduce the inside diameter. And it's also going to penetrate the surface to some extent. So this is light blue represents the anodizing process. So it's reducing the inside diameter of your hole. So I point this out because I want you to keep in mind when you're designing geometry and doing your engineering drawings, realize that there's some finishing process that affect the dimensions and tolerances that you're applying on your drawings. So even if you have a perfect dimension and perfect tolerance, and you overlook the fact that you are also specifying a finishing process that is going to affect those dimensions, the part may not work. It may not fit. A motor may not be able to go in. If it's a pocket, the plate may not go in because of the anodized buildup. Okay, so maybe maybe next week we'll address some ways to mitigate that, so to make that a non-issue. Okay, but for now, at least I wanted to mention that to you. Let's see. All right, I think we covered a lot. Let me see what else is left. I don't know if I'm gonna be able to finish the whole thing. Features to attach components. Last week, you'll see the replay at some point. I'll send out the email on YouTube regarding YouTube. We talked a little bit about split clamps and of clamping approaches. I was hoping to cover that today, but we're out of time at this point. Okay, really quick, let's cover this. This is critical. If you're designing, you have to get creative and make sure that you pay attention to accessibility to the threaded fasteners. So pretty often, what you will see is geometry such as this one. Let's see, let's go this way. brackets and things like that may have this kind of geometry, because over here, this L shaped is there because we need to add holes for our threaded fasteners. Okay, so the threaded fasteners would go in there and attach to whatever the base plate is. So here is pretty straightforward. You have plenty of room for the tool, for the fastener, for the hands of the person or operator or yourself to assemble the threaded fastener in place. There are times when it gets a little bit more challenging. Let me give you it's sort of a generic geometry just to give you an idea. Let's say we have a bigger block. Maybe something like this. And this block has, how do we do this? Let's say it's got a huge cutout here and another cutout here. Notice the rounded corners, not only because I can't draw well, but because it's designed for machining. And these cutouts go all the way through. So how am I going to sketch this? I want to get the point across fairly quickly. So let's say that huge cutout goes all the way through, and this one here goes through to that hole, okay? And for some reason, it just goes all the way through like that. It's just a generic shape to get the point across. We need to secure this down on a base plate. Well, you might be tempted to do this flange approach over here, right? To design in flanges so that we can have holes to attach it to on the bottom, to the bottom plate. Okay, maybe that's okay. Every application is different. Let's say it's not okay to do that. Let's say you want to save, I don't know, for whatever reason, this approach is not acceptable. Okay, there could be multiple reasons for this. Let's say the threaded, we're not able to add flanges, and it has to be a rectangular block. Okay, if that's the case, it could be that you think of the following. Let's add holes here. I'm gonna add a couple of holes here. And those holes are socket-head cap screws, 4 socket-head cap screws. So there's the counter bore, and there's the hole that goes all the way through for a socket head cap screw, right? And you remember what those look like. If not, please. But it's got a cylindrical head, and then the threaded screw portion, okay? So these guys are gonna go in there, 2 of them. So you got to realize, okay, now there's not much access for the threaded fastener. The person has to, you always have to keep in mind also with accessibility issues, the size of the person's hands, the fingers, etc. You can't assume that somebody with small fingers is going to be assembling this. You have to design flexibility for any type of normal human being. So now, bear with me, this is going to be a hand. Just really quick. We have a hand like that, and then we have the tool. We have the threaded fastener, and we have the tool, and we have to somehow angle the tool in there to be able to secure, to fasten those threaded fasteners. Well, one thing you can do is, if it's absolutely necessary, maybe you can make it work, but you got to think of user friendliness and design for assembly, design for manufacturability. So if the design permits, an alternative to this would be to drill out a couple of holes up here, just large holes, access holes for the tool at least. So maybe there's enough room for the fingers and to place the fasteners in there, but it's uncomfortable to get the tool in there, or it won't go because it's at an angle. You're not able to drive the screws. So with this modified approach, you've provided access holes for the tool. Now the tool can go through here and tighten the threaded fasteners. Okay, so this gives you a little bit of a tip. Unfortunately, we don't have any more time to cover a lot more and get more clever. But I think we covered quite a lot in about almost 90 minutes, 45 or so minutes. Let me know if you have any questions now. Do it quickly. I do need to cut this a little bit shorter today. I do have another commitment that I have to attend to. But if any last minute questions, let me know. I'm looking at the chat. And if you don't, the person that asked about welding versus threaded fasteners, please remind me or send me an email, and I will happily respond in a little bit more detail. But today, I'm sorry, I don't have more time to respond regarding the pros and cons between welding and threaded fasteners. Or you can ask me next week. I should be able to address it there, spend a few minutes addressing that. All right, you guys, I don't see any questions. So thank you so much. My pleasure once again to be here and work with you. I hope you found some benefit to this. Please remember, share with your colleagues, let them know this is going on. The more people, the better. I want to do my best to deliver this kind of value to as many people as possible. I think you guys can help me make a positive impact if you help me spread the word about these lectures, okay? So, okay, I will upload the other lectures to YouTube as soon as I can. Maybe I'll have somebody else do it, that they usually have more time than I do. My pleasure, Shane. You're welcome, everybody. Take care. Have a wonderful rest of your day and wonderful weekend. Okay, bye-bye.